Hello everyone, I'm Shaofeng from Peking University. I'm going to talk about streaming Euclidean max cut, dimension versus data reduction. This is a joint work with Xiaoyu, Chen, and Krauthgamer. We consider the Euclidean version of max cut. In this problem, we are given a set of points P in Rd, and the goal is to find a subset of points S, such that the cut of S is maximized. Here, the cut of S is the sum of distances from S to the complement of S. We consider the geometric streaming setting for the max cut problem. This setting was first introduced by INDIC in 2004. In this setting, the input is a set of points in a discrete grid in d dimension. So this is basically to make sure we can store the point efficiently in low space. And the points are presented as a stream of insertions or of deletions. For instance, in 2D, if we insert a point at coordinate 0, 1, then insert another one, 1, 2, then delete the first point 0, 1, and insert the point 1, 3, we will yield a data set P of points 1, 2, and 1, 3. And our goal is to compute an approximation to some optimization problem. Here we basically talk about max cut, which is a maximization problem. So we define the approximation ratio as opt divided by the estimation value E. So note that we cannot afford to store a whole solution since it could take a linear space. And this forces us to consider the value estimation E. Based on the current study, it turns out that the dimension D is a key parameter, and there are space regimes with respect to D. So the first one is the low-dimensional regime, where an algorithm could use exponential in D space, and these algorithms are only useful for low dimensions. Because if D is a super constant, let's say log n, then exponential in D is already poly n. Then for high dimension, the ideal space is poly D, since this is not much more than even storing a single point in the discrete input grid, delta to the D. And finally, there's also a weaker regime than the ideal poly D one, since the algorithm uses n to the epsilon poly D space. This space is still useful for high dimension. Now, let's briefly mention the research progress in these regimes. For low-dimensional regime, since we are allowed to use exponential in D space, it is not surprising to see many 1 plus epsilon approximations. Notably, we already know 1 plus epsilon approximation for max cut, MST, and facility location. Those are fundamental optimization problems. However, it becomes much more difficult in high dimension. For a long time, the only technique, or the achievable ratio from it, is from the distortion of the tree embedding. In particular, an early work of INDIC, who also proposed a geometric streaming model, gave order d log delta approximation for a bunch of fundamental problems, including MST, matching, and facility location. And little progress is made since then. Now, even until 2022, the ratio is slightly improved to log n for MST, and this is still about the tree embedding gap. Indeed, the big issue here is the large omega-1 ratio from the tree embedding. Interestingly, recent works can break this fundamental barrier of tree embedding and obtain several improved results. If we use the ideal poly D space, then we obtain order d over log d approximation for facility location. And if the weaker n to the epsilon space is allowed, then even constant approximation for both MST and facility location can be obtained. However, all this progress can only give constant approximation at best, and it is interesting to see whether one can do 1 plus epsilon approximation for fundamental problems in high dimension. Then comes our study for max cut. In fact, for max cut, it is already possible to obtain a 1 plus epsilon approximation using a dimension reduction result, combined with the previously mentioned exponential in D space 1 plus epsilon approximation streaming algorithm, one can obtain the poly D space algorithm. However, this only gives a space exponential in 1 over epsilon, because exponential in D is exponential in poly 1 over epsilon. Our result, on the other hand, achieves the same 1 plus epsilon approximation while only use poly 1 over epsilon in space. Approach-wise, we use a subsample or data reduction approach, which is conceptually related but also fundamentally different from the dimension reduction. Even though the dimension reduction is not new and is not the focus of our work, and was first proved in a paper by Lamerson et al., we still decided to talk about it, and we give an alternative simplet proof of it in our paper. So essentially, the theorem says that a black box use of the Johnson-Strauss transform with a much smaller target dimension of only poly 1 over epsilon already suffices to preserve the max cut cost within arrow 1 plus minus epsilon. So note that this is very powerful, since the Johnson-Strauss transform is data oblivious and readily applied in streaming. But wait, isn't it true that the Johnson-Strauss transform is tight and has a target dimension omega log n? How come we can achieve a much better target dimension for max cut? The trick here is that the classical lower bound for Johnson-Strauss is about preserving all pairwise distances, while for us, we only need to preserve the max cut value, which is a collective quantity instead of the pairwise distance, and is much weaker. So, in fact, what we can show is an additive error of epsilon times the sum of pairwise distances. This, even though it's a large additive error, it already suffices for max cut, since max cut has a lower bound of 0.5 times the sum of pairwise distances. And therefore, this dimension reduction also generally works for problem with a large opt. Now, what's new in our alternative proof compared with the original one by Lamerson et al.? We basically make a black box reduction to a strengthened version of Johnson-Strauss guarantee. Specifically, on top of the pairwise distance, we also require the expected error to be well bounded, as shown in this red font. This second guarantee is not too strong, since the standard Gaussian version of Johnson-Strauss construction satisfies this property. However, it has interesting question to see whether this second property also holds for other variants of Johnson-Strauss, such as the sparse Johnson-Strauss and fast Johnson-Strauss. Finally, as we mentioned, if we combine the known algorithm for max cut in low dimension with the dimension reduction, we can readily obtain a 1 plus epsilon approximation. This approach has both a weakness and a strength. The weakness is, of course, the space complexity. It is exponential in 1 over epsilon. But what is stronger is the guarantee. And this comes from the low-dimensional max cut algorithm. So in this algorithm, it actually returns a cut oracle f, which tells us whether a given data point should be put in the subset S or not. It has an interesting open question to improve the space complexity of this cut oracle to poly 1 over epsilon. Now, let's go into our main result. Essentially, we improve the exponential dependence in 1 over epsilon to poly 1 over epsilon for 1 plus epsilon approximate max cut. Furthermore, we obtain a lower bound which rules out the exact computation of the max cut even in 1D. So this basically means 1 plus epsilon error is necessary. Our main technique for this new bound is geometric sampling, implemented where randomly shifted quad tree in streaming. Before we talk about the streaming algorithm, we prove a general data reduction theorem for max cut. So essentially, this theorem says that if we sample every data point x with a probability proportional to q of x, which is defined as the sum of distances from x to every other data point, then the max cut on this subsample is within 1 plus minus epsilon to the original max cut. In addition, this sampling is robust, and the error of 1 over lambda of sampling probability, which is larger than 1, only translates into poly 1 over delta in the sampling complexity. Hence, we can afford an error of polylog in the sampling probability, and it only adds an polylog factor in the space complexity. So intuitively, this Q of x, which is the sum of distance from a point to every other data points, is roughly the contribution of x in opt. And this could be viewed as an important sampling, and this subsample could also be viewed as a core set. But how to implement this in streaming? Well, this is non-trivial, because classic sampling tools in streaming, such as L0 sampling, is mostly defined on the frequency vector. However, this frequency vector does not use the geometry, and hence it is not suitable for our geometric sampling. In fact, this lack of sampling tools is a general challenge in the study of geometric streaming algorithms. Our technical contribution is a new sampling tool that samples roughly with the probability proportional to Q of x, which is the sum of distance from x to every other data point. This sample is very intuitive, and we believe it may be of interest to other applications. Interestingly, our sampling is actually run on the quad tree, which as we see has a big distortion. However, the trick here is that this distortion only introduces error in the sampling probability, which ultimately appears in the space complexity only, rather than the ratio. And we have to note that if we directly use the tree embedding to embed the whole instance into a tree and solve the max cut on the tree, we must suffer this omega d log delta distortion of tree embedding. So let's briefly recall the tree embedding. The tree embedding that we use is from INDIC. So we use a randomly shifted quad tree as a tree embedding. So in particular, we first find a bounding box of the dataset. In this case, is delta to the d, but we have to use a slightly larger one, which is 2 delta to the d. And we use a random shift to every d coordinates of the bounding box, uniformly at random. The tree is then built with nodes as the squares in the quad tree, and the data points lie on the leaf. For every node of a side length 2 to the I, it connects to the parent with an edge of length square root d times 2 to the I. We shall then use the tree distance, denoted as dist sub t, as the approximation to the original distance dist. And the key guarantee is that this dist t is dominating the original distance. And furthermore, the upper bound is that for every pair of points x, y, the expected tree distance is at most d log delta, order d log delta times the original distance. Then the idea is to sample with respect to qt, which is the q value on the tree. So one can first show that the sum of qt's, which is going to be the normalizer or denominator of the sampling probability, is well preserved. So this is because this q is basically a sum of all the, this capital Q is a sum of all the little q's, and this is a common denominator, and we don't need a union bound, and we only need to use a Markov inequality to show that with the constant probability, this capital Q, the sum of little q's, is within order d log delta to the true value. So then comes the important part, which is to sampling with proportional to qt, little qt. So we first observe that this little qt has a nice structure in the tree. In particular, for a data point x, which must be a leaf, the path from x to some y that is located in the level I sibling of x must cross the level I ancestor of x. So that's why we have this n minus ancestor of x, ancestor I of x term. So this is basically the number of points in the level I sibling. And basically, okay, so the number of points not in the subtree of x, level I subtree of x. So examine the formula for qt of x more carefully. We can see that if the level I subtree of x is smaller than some constant fraction of n, let's say half n, then the contributing elements n minus ancestor level I of x must be omega n. Since we only aim for a constant approximation, so we can round this n minus the number of points in the level n ancestor of x as n. Hence, for every x, there is some critical level I such that the contribution larger than level I can be easily approximated as n times beta I. And this is only a constant factor to the true value. But the remaining part must be the same. So now we need to find this critical level for every data point x. To do that, we first define hj as a node in the tree which contains the most data points in level j. So as in the picture in the top of this slide, the red circles are the hj's in each level. Basically the points are the node that contain the most points. Now let L of x be the critical level, which is the max level j such that the level j ancestor of x is hj. You can see an illustration in the picture. So basically, we show that we can define only order log n estimators, which corresponds to the levels j's, and this only uses the order log n information of hj's. And we show that the qt of x is approximated by the estimator at the critical level L of x, which is which can be sort of computed much more easily. So finally, with this simplification, our eventual algorithm first samples a j, or say hj, which is a square, then sample a data point x uniformly at random from this square. So these require several other estimators and some subroutine in streaming, and we omit the details. So we conclude with two future directions. The first one is to improve the space complexity of the Carter oracle. Recall that a Carter oracle is a streaming algorithm that, given as a query a data point x, it returns whether this x should be put on the left or the right of the cart consistently, so that if you query all the data points to this streaming algorithm, you obtain a max cut solution, which is 1 plus epsilon approximate. And the current result for Carter oracle is basically using the dimension reduction, and it only achieves the exponential in 1 over epsilon, exponential in poly 1 over epsilon space. So the open question here is, can we close this gap and improve it to match the value only result, which only uses space poly 1 over epsilon. So the other direction or technical question is to justify the tightness of the importance sampling theorem. Recall that in the importance sampling theorem, we see that one needs to draw roughly 1 over epsilon to the 4 number of independent samples with respect to the distribution proportional to the q of x, which is the sum of distance from x to every other points. But is this 1 over epsilon to the 4 tight? Can we improve it a little bit? That's all for my talk. Thanks for your attention.